Can you hear me now?
Yes, you're on.
Okay. When I shared the screen, it seemed to shut everything off. Let me try again.
Yeah, crossing my fingers.
Can you hear me now?
Yes, we
There,
hear you and we see the screen.
and you see
Lovely.
the screen.
And you still have a bit more than your 30 minute, wait, hour actually. So you have your hour.
Okay. Um, Thank you for everyone coming. Um, I want to start off by saying that I'm going to go through a little bit of history so people have the background. Um, this work was originally done um, several years ago for the Canadian Space Agency. Um, Louis Grenier came to see me when he was the head of strategic planning for the Canadian Space Agency. And I had just finished creating a robotic mining pilot scale operation at INCO in Sudbury. And so the idea was to look at what we had already done in terrestrial mining applications and look at the robotics work as well as the actual how would you create a mine. Um, I have, in my background, fairly extensive experience. I'm a PhD mining engineer. Used to be the head of research and development for INCO globally in mining, um, and have subsequently worked in many other fields that range from robotics for mining to robotics for farming to uh, telecommunication systems for robot control and others. Um, the other authors, Brad Blair was someone that worked quite extensively in the Lunar Mining Initiative and had a lot of background that helped us when we put this strategic plan that the CSA wanted together. Um, Recently, um, within the last 2 years, with all the interest in lunar mining, the Canadian Space Agency approached me again and asked me to update the work. And so we took what we had done and wrote a paper for it, and then updated the paper to 2023. At that time, I got uh, Dr. Jim Logan and Dale Teets involved in it, and Dr. Basiri. That Jim was involved in it because he was responsible for tracking all of the astronaut health over their careers from the Apollo missions. So he has had very extensive knowledge of the astronauts that had actually gone to the lunar surface and what health issues they had. If you listen to Jim and to Dale, one of the things that you'll hear them say constantly is in each moment you're on the moon or on your way to the moon, space is trying to kill you. And so you have to be extremely careful in how you approach any work around this. So that drove a lot of the work that you're about to see. And Dr. Basiri and I have been colleagues for many years, and he works with me constantly on the robotics work. So I want to start with this picture. For those who don't know, I live in a place called Sudbury. Um, it, and we've been mining the largest asteroid hit on the Earth for the last almost 200 years here. We constantly are doing exploration, mining, processing, and making mineral-related products. Those range from nickel out to the critical minerals that everybody's looking at for today around batteries, but goes far beyond that into many different minerals. When I started my work at Inco, I was asked to transition from mechanized mining to robotic mining as the next paradigm forward. So I found it very interesting because we were working on tele-autonomous operation techniques mining this asteroid. As I left the university or left the company, several people from the US, the National Science Foundation, and others asked me to get involved in orbiting space solar power and other things because of the extensive work we had done in teleoperation and communication systems and positioning systems. And this talk is going to basically reflect what we've worked on in the past and how that's gradually gotten a lot of play. I've been working in the mining industry for my entire career of 40 some odd years, and I've been working in the space industry for 25 years. And so, but most people will see me as a mining person and a robotics person more than a space person, which is something I think has a fair bit of value. So I want to show this so that people can see what's been done. Terrestrial robotic mining, the mining industry is not, it's a gradual industry because of its nature. We've been mining on Earth for millennia, and we have a saying in mining that if you can't grow it, you have to mine it. What's interesting about lunar robotic mining is it's very difficult to grow anything on the moon unless you take care of it. So we began working on how to automate underground mining as far back as 1988. And a lot of that work went to building computer networks that will allow us to run mining robots. Even in that time period, we were already working on artificial intelligence for mining control based on insect behavior theory. In 1992, the picture you see on the right is a demonstration of the first teleoperation of mining equipment that was done. And what's important about that is that it was done in front of 1,700 people in Toronto. And it had one operator, the gentleman sitting at the bottom, Chico, running two machines underground, 4,000 feet underground, getting situational awareness 400 kilometers from between them. It had a 35 millisecond latency, and that allowed us to let the operator run two 36-ton pieces of equipment in real time doing that work. Based on that work and this video, we were able to have one person run multiple machines across multiple mines. This is one of the mines that was located 20 kilometers away from that command center. And this is the video feed from operating that mine. What's interesting about this is that we've actually already been able to deal with the equivalent delays of going to the moon for teleoperation of mining equipment. And so we're able to do exactly what you see on this screen between the Earth and the moon, which is going to become quite important, as you'll see in the presentation. That video caused the development of a project, which is the mining automation project that we conceived of, that ran between 1995 and 2000. It involved, at that time, Tamrock from Finland, and Sandvik out of Sweden, our company Inco, Dyno Nobel of Sweden, and the Canadian government. Once that pilot scale project had proven successful, that's when the Canadian Space Agency approached myself and my team to build a strategic plan for mining the moon. And so we began a 2-year journey between 2003 and 2006 to build that plan. It was quite intriguing because we presented that plan at the American Institute of Aeronautical Engineers, and nearly got laughed out of the room talking about underground mining facilities. What was more intriguing was that Dale Teets, who is on the call today, he and the team at Shackleton Energy came to me and asked me to lead their mining effort for building the first lunar mining operation on the moon. We did that, and I'll show you some of the pictures of that work in the presentation. And then it kind of sat in a hiatus waiting for, it was an idea ahead of its time, and it was waiting for people to catch up to it. And this republishing I mentioned earlier of the CSA lunar mining plan in Algar was updated and put in and sponsored by the King Abdullah Research Institute just recently. But that incorporated a lot of the medical issues into it that needed to be dealt with. And I encourage everybody to read that document, because it is really quite different than what NASA and other people are proposing. But it's really a plan for not only how to mine the moon, but to go on into other planets like Mars. So I'm going to first of all go through some of the things that were accomplished. You saw the video. We were doing this kind of drilling where one person was running 3 drills to be able to work in production on Earth. But what's fascinating is that JPL came to visit this work to justify their Pathfinder mission to put a drill onto the Pathfinder, and subsequently now every piece of NASA equipment that's going out to do exploration has a drill on it. In my opinion, an insufficient drill, but they are at least beginning to sample the rock. And I'll talk more about that as we go on. That system has remained in production and was just until 2018 when it was shut down. I want to say this so that people understand the amount of investment the mining industry has made into it. This investment you see in front of you was just the investment done by Inco at the time, which is now Vale. Between that time period, we put a nearly $50 million investment into creating all of the work that you see here. And when you include the research mine that was established in 1995, that investment moved up to $250 million of research and development. So everybody understands that really dwarfs any mining research that NASA and others have been done. The industry is far more proactive around doing that work than the space program. And you'll see in a minute why the mining industry is likely going to play a very significant role in the creation of a lunar outpost and mines on the moon. That work consisted of creating high bandwidth networks to be able to run the underground mines, which are patented, subsurface positioning, and several key mining robots that allow you to create the tunnels and the production systems. In the terrestrial context, they were achieving a 10-to-1 savings in labor. There were many types of robots, and there were over hundreds of man-years of teleoperation experience created. This is the some video of the pilot scale project that was achieved on the final day with all the different types of equipment and the teleoperators running the work. Subsequently, it carries on past that into today, and now we're building robots for extreme safety conditions. And so this particular project that you see here was built to try and recover an area in a mining operation where there was an explosion that nearly killed 3 people. And they needed a way to robotically dismantle the explosives pattern from a kilometer away. And so we continue to work in those fields of high capacity networking, advanced sensing, pattern recognition, and cooperative robotics. And so that's an extremely important area of work that we do, which is being done by industry as opposed to space in general. One of the really important technologies that has been developed for mining is this M3D2. And yes, it does look like R2D2. There was a reason for that, because we were looking at how we would take robots like that and embed them in mining equipment, all the systems that are on board, because we're doing essentially IoT, the Internet of Things for mining. And you can see in the video that's playing, we need to be able to go in and map and do pattern recognition and various things on the rock itself. And so these are all crucial technologies for making lunar mining a reality. This robot, the orange one in the back, which I'll show you more of, is one of the first real significant applications of IoT to robotic mining. We use a new patented optical communication combined with Wi-Fi to be able to run that robot. this is not your rumba. This is a small equivalent to a tank. That is what you need to be able to do true mining work on different planets and in different areas. That robot was designed to do IoT, which we've coined a term called metamining, because we're really using data about the mine to run the equipment. That arm is the Earth-based equivalent of the Canadarm. It reaches out 30 feet up and out 15 feet, but it has all of the systems of networking, which you see the optical communication on the unit, the arms, drills, teleoperation control, that's all done from the truck that I showed in the previous slide. And this unit was deployed in Chile for a company by the name of Codelco to try and save lives today because of the amount of these rock blockages they get 30 feet up above where people can't go. This is another video of the unit, just so you see it, with the arm extended, ready so that people can understand what we put together. So now I'm going to turn to lunar prospecting, mining, processing, manufacturing, and settlement. What most people have done so far is they've seemed to have only really concentrated on water and not looked at the moon for its potential in a cislunar economy. And I'd like to talk a little bit about what kinds of things we are really looking for and at. We need to know, as we move into the future, what is economically available to mine. Water is important because water can be broken into rocket fuel. Helium-3 is going to be important as it's going to become a fuel for fusion reactors. Base metals are going to be needed because a lot of the things that you have up on, that you want to do on the moon, it's just going to be cost prohibitive to bring the metals from Earth. And so a lot of things like building mining equipment and some of the various things are going to be, I believe, done in underground bases on the moon. Precious metals are economic to not only get on the moon, but to bring back to Earth. And so there's potentially a business in that, which with some proper branding may be quite a valuable business. And the final one are new minerals. The Chinese have been exploring on the back part of the moon, and they've already found at least one new mineral. I believe, and I would have to look more deeply into it, but I believe I've heard of 3 altogether. But the most important one they found is a new mineral called changelite. And changelite is a helium-3 mineral. Before I go on in the slide, I want to talk about helium-3 a little bit. Helium-3 is worth a tremendous amount of money on Earth, mainly because you can only get it through plutonium production. Helium-3, based on cosmic and solar radiation on the moon, is abundant in comparison to Earth. And so, in my opinion, as a miner, there's going to be a gold rush equivalent for helium-3 on the moon. And it's going to be the thing that will drive a lot of people towards investing significant money into to lunar operations. I want to talk now about a couple of important facts. One, all minerals on the moon are igneous in origin. I got into a large debate when we were with Shackleton with a gentleman by the name of Paul Sputus, who I enjoy tremendously. Unfortunately, he's passed away now, but Paul and I got into a pretty massive debate and about lunar minerals. And I said to him, you know, we know everything there is to know about the moon when it comes to slag. But I said, we have no idea what the actual body of the moon is because we have not put a drill hole into the moon to try and determine what the characteristics of the lunar surface really has out there. That work is going to be crucial going into the future, just as it is on Earth. At this point, there are no sedimentary rocks on the moon, but I would also argue that if the moon was created the way that scientists believe, and it was a piece of the Earth that was broken off, there is the potential for sedimentary rocks and for finding things in the crust of the Earth, or the crust of the moon. I want to digress for a minute so we all kind of understand that in Scientific America, there's an international drilling program, which I was a part of, and we funded a hole in northern Russia around the Kola Peninsula. That drill hole went to 45,000 feet underground. It's the longest drill hole ever done on Earth. One of the most important things to get out of that was near the 45,000 foot mark, they found fossilized crustaceans. Well, I don't know that that's going to happen on the moon. I would say to you, nobody on Earth thought we were going to find fossilized crustaceans at 45,000 feet underground. I would also say to you that I have personally worked with a guy by the name of Steve Scott, and Steve was one of the three who went to the Marianas Trench in the submarine with Bob Ballard. And Steve and I had a lot of discussions about what they found because Steve was a geologist and he went down there thinking they were going on a mission to look at geology. And what they found was a whole chemosynthetic world with life. Life that included tube worms and crabs and fish that had no exposure to light. And so they found a whole new ecosystem. And that correlates to the fossilized findings of the Norilsk drill hole. And so it, in my mind, changes a lot of things about what it is can happen on the moon and happen on other bodies in our planet. One important point that I want to say, on Earth, I was talking with a geologist buddy of mine just last week, and geologists are looking for craters to find mineral deposits on Earth. Problem is, most of the craters are weathered and they're metamorphosed. The interesting part about the moon is none of that has occurred. So we know precisely where to look for minerals and metals on the moon. And it's in and around the outsides and the insides of the craters. And so exploration on the moon should be a lot easier than on Earth. Another important point about the moon is 1/6 gravity opens up a lot of opportunity to mine at depth. The technical depth on Earth is about 4,000 feet. There's some mines deeper, but in general, that's the technical cutoff. With 1/6 gravity, the technical cutoff is closer to 6 times that. So 24,000 feet of crust. And so the moon actually has significantly more mineralization available to mankind than people think. I want to talk a little bit about who our customers will be, because I look at this from a business point of view, not necessarily from a science point of view. In the short term, it's going to be things like science and security and commerce. But in the long term, security and commerce are going to take the day. And so we're going to see an evolution in what kind of things are going to take place on the moon. But I believe because of the structure with no real living life on the moon, that mining is going to be extremely key to the moon's future for Earth. So why is this attractive to miners? This graphic to me is extremely important. When you come from Earth to low Earth orbit, it costs roughly $10,000 per kilo. And when you go to geostationary orbit, it costs roughly $50,000 per kilo. But when you look at the value of minerals coming from the moon to those two locations, which are arguably the next most important places the Earth-based technology is going to build, you notice that the prices drop quite dramatically. $500 per kilo to low Earth orbit and $250 per kilo to geosynchronous orbit. When a miner looks at that, they say, if we put the capital into the moon, one-time capital, it makes a lot of sense to be able to go and mine the materials there because it'll be a lot cheaper to build things. Now, there's tremendous changes going on in technology. Some of the replacements for the space station are going to get launched, and there's going to be medical research and medical factories put into low Earth orbit and geostationary orbit that are going to start to become major commerce. And without a supply of cheap and abundant materials of all types, that is going to get limited. And so current Earth-based mines will have a hard time competing with lunar mines. And so that's a really important slide to understand as we go into the future. Now, this is a slide that Jim Logan provided to me, and it was the main slide in a NASA report that he was involved in. And it covered, it had that graph in it, and I'll explain it in just a second. But what are we up against? Radiation is absolutely the showstopper. And I discuss these as showstoppers, and I'll explain why. If you talk to Jim, people will only be able to work underground on the moon or in cover doing what it is they're going to do, because without strict control of the radiation dosage, there may be short sorties onto the lunar surface, but we are not going to live and do things on the lunar surface except with robots. Second, gravity is, as much as some people think it's an advantage, from a mining perspective, it's a disadvantage. You cannot get the forces you need to drill and blast and all those things without figuring out how you're going to manage gravity in in a more important way. I happen to believe that going underground allows you to do it because it's what we do today. Temperature is going to be a massive issue. 30 Kelvin or 230 degrees C. That's 3 times colder than anything we've worked with on Earth for mining. And I'm reminded of a presentation I did in Baltimore where all the space people came in and they talked about it. And I asked them if they actually understood how much wear and tear is involved in mining. And it's going to be worse on the moon than it is on Earth in terms of wear and tear. And so the consumable side of what it is that's going to happen on the moon is going to be quite dramatic. And lack of atmosphere is another huge showstopper. And so we're going to have to create a way to have atmosphere. I believe those reasons are the reasons why we're going to be underground in a lot of the work we're doing. Now to this graph, just quickly. Those red arrows show the times when the Apollo missions were in space. These long lines here show the massive radiation events. As Jim Logan put it to me, he said, this graph represents NASA's Department of Good Luck as opposed to good management. Those astronauts came extremely close to dying because each one of those events would have killed an astronaut in a capsule. And so we're just very lucky, or NASA's very lucky that no one was hurt in those time periods. That's the reason why we need to get under rock cover as quickly as possible on the moon. So I want to talk a little bit about lunar prospecting. Lunar prospecting, we've developed strategies. One of them is, and this is the list, we need to look for orbital deposit identification, just like we look here on Earth. We need to assess the targets that we find to prospect them, and that's going to all be done robotically. We've got to sample outcrops to determine their potential, drill out the potential deposits. And I will say to you, as of yet, there are no lunar drills that can drill, and I'll explain a bit more about that in a slide coming up. Determine the economic viability, and it's a vast celestial body like here on Earth. This is a diamond drilling scenario that I ran for the company. We don't have any of these drills yet for the moon or for Mars or anywhere else. The total amount of drilling that Paul Sputus and I argued over is I think we've got a grand total of about 3.5 feet of drilling into the lunar surface. When I did this kind of work inside of INCO, we were doing 750,000 feet of drilling per annum just to keep and understand what the ore bodies look like. And so in mineral exploration, it's far different than scientific discovery. We're charged with finding, proving economically viable quantities and qualities of material, determining the rock characteristics so we can build things, and then providing that information to people. This is an initial plan. The beginnings are going to be done through telecommand centers on Earth because we're not going to have a lunar base done until we get some of this rock characteristics. So the teleoperation systems are going to be important. There's a bit of a scenario around the kind of landers and deployment of robots and what this robot would look like. I've intentionally not put in the innards of that robot because there's a lot of things that we do in the mining industry which are highly confidential, and they're all embedded on the inside of the plan for those robots. But this is the information we need. Satellite information allows us to determine the geology as you see it in this picture. We need to know where the faults are in the moon, and then we need to be able to look at whether other excavations there are and determine how to mine it. Whether it's a surface deposit like the one up above, if that's all we want to look at, or if we want to go to depth in the lunar surface. And then we have to work out the tunneling scenarios to accomplish the task. Following prospecting and exploration and delineation, we have to select an outpost. And you see in the background here an initial concept that was in the CSA plan for a first lunar outpost in the side of a crater. We have to establish power infrastructure, oxygen manufacture, communications, robotic equipment, and processing equipment to make metal. We have to build mines and launch facilities, a moon outpost, and tunneling and production systems. This was notionally taking into account the challenges of the showstoppers, how we would build a landing area on the moon, and then what the earthworks and the rockworks would begin to look like for a lunar base. We have absolutely no idea where to put that yet, because we will only do that kind of work once we understand what the prospects are for deposits. The next few slides are kind of scenarios of the pieces of equipment. Obviously a digging machine, a drilling machine, a scraper that duals as a truck, and then an initial terrestrial control center for running this kind of operation. Lunar mining deployment, and so this is just as you scale up the kinds of things that we would have to do. Lunar equipment deployment, initial construction, and the kinds of things you see on there. A sintering robot, that was one concept we had for getting the dust managed. And there's a fair bit of research gone into that, which I can share at a different time. And then finding the right spot to create an underground entrance, whether it's a lava tube entrance or whether it's a full-blown portal like we do normally on Earth. We have to find the right entrance, and then we have to excavate it to the needs. This kind of thing is what we do on a daily basis here. So I've said it in Sudbury, there is somewhere around 1,000 miles of tunnel underground. And I would expect as time goes on, we'll see that kind of thing on the moon. We'll excavate the rock using all these various tools. And these are robotic equivalents of what we already do. One important piece is that we would launch these portal airlocks to be able to have a way of pressurizing and certifying the base. We're assuming in this there'll be a limited manned base because of the level of maintenance that will have to be done. We would install that, roll it in, and then be able to seal it. Once we can, then we can create a facility to certify it for human habitation, go inside the portal and begin to work our way down to the deposit that we want to find. In the short term, solar power will make sense, but in the longer term, we're going to have to move to things like nuclear power and do things for habitat, cooling and heating. Interestingly enough, things like heat pumps may actually be of something we can look at in a lunar context. As we begin to build up, we can expand underground, create command centers that work with the terrestrial one to begin to run the operations, and then begin to create the habitats, get the water and oxygen stored for what we need to do. And we have all the issues that come along with people being there. As I build mines for the Arctic and places like that, this is not unusual. And what we are always trying to do is minimize the personnel in the field. And so this particular is for emergencies where we would have situations where you'd have airlocks for people so they were protected if something went wrong. Different personnel quarters, and then a robotic mining center to be able to run the pieces of equipment. And obviously the standard stuff like latrines. Telecommunications is going to be absolutely crucial, and I do a lot of work in that area right now. We hold patents in a new style of communication that's capable of getting out into the terabits per second in future. CO2 conversion. And then once we get to mining, typically these are the mines on Earth that make money, and they will work on the moon just as well as on Earth. Even as we go and we look at the bottom of craters, this style of mining is probably going to be one of the most efficient, although we have robots for just about every mining technique that's out there. Gravity, thickness of concentration, all those things become issues that mining guys like us deal with. So in summary, and I've given a very high level view of this for people. These reports are hundreds of pages long, and it's hard to summarize them all into a few slides. But what we've tried to do is deal with the showstoppers and create what makes sense. This is a very expensive undertaking, and it has to be de-risked. And so I just want to show a couple of additional slides of what de-risking potentially looks like. We have to de-risk because of all these issues of weightlessness and extreme temperatures and all those things. As we begin to launch this kind of equipment, we've got to be knowledgeable that it's going to work, because we're not going to launch it in an experimental fashion. We put together a slide, Dale and I, a couple of slides around a lunar thermovac chamber on a much larger scale than NASA's even, or the CSA or ESA are considering. And so this kind of facility would need to be built in Canadian Shield or similar rock types, but we're looking at a thermovac chamber that would have the ability to allow robots to work underwater in partial gravity areas, and also be 200 or 300 meters deep. And so this is what that kind of facility has the potential to look like. So with that, I've got 5 minutes left for questions, I think, if people are interested.
Thank you, Greg. And yeah, you have 15 minutes actually left for questions because you started early.
Oh, okay.
So we do have some questions that have been asked in chat in the meantime. But if anybody wants to pop in and just ask a question, we can start by that, and then I'll pull up the from the chat later. Okay, we'll take something then in the meantime. Anybody feel free to pop in and talk, and I'll start stopping people if you talk in across each other.
Yes, I will start talking then.
Yeah,
A
good.
really great presentation. I learned a lot. Thank you for your time on the research. I have few questions.
Sure.
So number one is what are so for the radiation on the moon versus Earth, like how strong it is on the moon, and how can we protect our astronauts from the radiation if we're building settlements?
Well, I think I'll do my best to answer it. If I wish Jim was here, but essentially, you're in direct solar and cosmic radiation on the surface of the moon. We're protected on Earth by essentially having the equivalent of 10 meters of water between the space-Earth boundary. So protecting astronauts needs to have the equivalent of 10 meters of water between the person and the outer environment. It's partially why Jim and I have speculated that it's likely that most of the work will have to be done from bases inside of the rock. Even a lot of the habitats that you see people building up, they're not thick enough and they're not dense enough to protect people. So, you know, I was at the Mars missions in Flagstaff, Arizona, and they have this wonderful machine that kind of looks like an ant to do geology with. And when I got back, I didn't know as much about radiation as I do now. And Jim called that NASA's radiation dosing concentration machine. He said nobody's going to go in there and actually work with that because it's too dangerous for people. And you know, I come from the world where I'm used to working in underground uranium mines and what we have to do to protect our personnel around that. And so you know, it's not a little bit of protection, it's a lot more. So does that answer your question?
Yes, I learned a little bit more. And maybe last question. Uranium, I mean, I have master's in biochemistry and molecular biology, my first master's.
Yes.
Later I studied electrical engineering. So uranium, again, the differences about nuclear energy future on the moon versus Earth, what we already have.
Yeah, a lot of differences. I'm not a nuclear expert. I'm a user of technology. So I would look at putting stuff like that in, and I would say to you, in my world with micrometeorites and larger meteorites, I would put a facility like that underground to protect it. I think most of them on Earth should be underground to protect them, but we tend not to do that. So it would be more so on the moon than on Earth.
Wow, okay, yes. Thank you.
Yeah.
Thank you. Thank you, Marufa. And then we have a question from Frida. If you unmute, you are unmuted, so please.
What is the market for helium-3?
I can't tell you off the top, but at the moment, I believe I'll have to get back to you to confirm it, but the value of helium-3 per liter is something in the order of I think $200,000 a liter. and the market is small right now. But once fusion reactors start becoming the norm, it's going to be the fuel of choice, and the market will go out of sight.
Thank you.
Yeah, I've heard, and I'm quoting that without knowing where it came from, that there are more energy in helium-3 on the surface of the moon than we have used so far as a
Yeah.
species. So that gives a bit of the scale.
Yes.
By the way, I should have started by saying that your presentation was absolutely marvelous. Really appreciated it. So
Yeah.
thanks a lot for that.
Yeah, no problem. It's the first time that it's actually been presented in years, because we never really presented it.
We're lucky to have you then.
Yeah.
Because that was a lot of things to think about.
There's also I saw one of the questions that was in the question panel was around getting the paper. The
Yep.
paper is in Elgar, published by Elgar, and it's in a book called Research on Energy Politics. And it's just recently been published as part of an initiative. So if people want a copy, they can get it there.
Wrong chat, that was. I thought I'd write that in the meeting group chat. Tips. I didn't want to say that. So it's Elgar. It's ELGAR. And research
GAR. Yeah.
on and research on energy politics. I put that in the chat for people.
Yeah. One of the questions that was interesting is around lubricants for drilling. And I just want to say that the need for lubricants for drilling are large on Earth, but mostly they're for safety reasons. And so if you're doing this robotically, your need for lubricants goes down quite dramatically, because you can drill dry. I think the larger thing around drilling on the moon is going to be, how do you bail the cuttings and get them out of the hole? That's not, the techniques done on Earth are different than will be able to be used on the moon, I believe. So there's it's not like there's not a lot of work to do yet in some of those things. There are significant work to do.
All right. I think we had some more on energy, thorium, but there is a fair bit of thorium on the moon, isn't it? I think I've heard.
Yeah, I think so. I haven't gone into that depth around it.
Huh.
Really, if you look at it, there's very little real exploration done on the moon. There's lots of scientific exploration, but there's very little mineral research done on the moon. There's some fantastic gravity graphs that give an indication of mineralization, but they only give an indication. So
So the first step should be to start prospecting on the moon rather than mining, of course.
Exactly.
Yeah.
Well, absolutely. There's a lot of work to do in prospecting.
Yeah. Any other comments or questions? Okay, then I think we'll go to the next. And again, thank you so much. It was a really great presentation. And I will struggle to do something in my basement along those lines. I'm making a lunar analog, and I'm going to have a mine in it, and I do have bedrock in the basement. So
that's cool.
It will not carry any ore, of course, but